Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Peter did his PhD there with Professor who's also visiting here, but we're not letting him out of NEO jail until this afternoon, so we won't see him for 2 hours. Peter's done work on high-speed database systems in support of OLAP applications, particularly exploiting details of machine architecture, and was chief architect at a company that spun off based on some of that work, research work that they did while they were Hillary, and went back to CWI as a researcher where he is now. He's done a variety of things on database system implementation, working a little bit on database support for consumer applications. But what we're going to hear about today is his work on database system support to make XQuery run very fast. So let me turn it over to Peter.
Thank you, Phil. Right. So, by the way, you can interrupt me while I'm talking. So please, if you have questions, don't hesitate. There's ample time, I think so. I'm wondering, are there people in the room? Is this all Microsoft Research crowd, or are also development people involved on the XQuery? Oh, okay. Oh, that's great. So, because I'm not really aware of what will be in Microsoft SQL Server 2005, but I'm aware of the fact that it will bring considerable XQuery support. So, well, probably what we do here is a bit different, but it might be interesting to take a look. So this is MonetDB Pathfinder, a system that allows you to store and query XML documents on top of a relational DBMS, in this case MonetDB. Next. Okay. So this is my plan for the morning. First, it's actually a combination of two projects, the MonetDB project and the Pathfinder project. So I'll introduce those first. This is also, or Pathfinder is the relational, is a system that can be classified as a relational flavor of XQuery, and I'll explain what that is actually, relational XQuery. I will give them some details on how it's, on the particularities of the MonetDB implementation, and then I'll go to some of the optimizations that we put into the system and highlight their effect on performance, and finish with conclusions. So, first about Pathfinder and MonetDB. So, for XQuery systems, I roughly see two kinds of approaches. So, either the tree-based or the relational approach. So, in tree-based approach, the idea is that in order to truly support XML well, you need to adopt tree data structures as the basic building block in your storage manager. And then typically have some kind of tree algebra on top of these tree data structures. So roughly the equivalent of the relational algebra on top of rectangular tables, but of course different. Some of these systems are quite database-like Timber, which does mapping of XQuery to tree algebra optimization, and then tree algebra execution. Some of them are maybe more simple. I call them navigational, things like Galax. Basically, they mostly do what the XQuery program tells them to do, just following for loops and kind of thing. So examples of these systems are Galax. Galax is an interesting implementation because it's so complete. So it's one of the best and fullest implementations. Other are Flux and Xhive. Xhive is actually a Dutch company that makes an XQuery product. We have some contact with them. So But getting back, so this, but this talk is not about tree-based XQuery systems. This is a relational XQuery system, and in relational XQuery systems, XML documents are threaded and stored in relational tables in a relational backend in a relational system. And XQuery queries are translated into relational queries, into SQL queries, for instance. So basically, there are two projects going on. Maybe I should go to the next. There are two projects going on. One is called Pathfinder. This is actually a project of University of Constance, of Torsten Grust. And they have been doing a lot of work in the past 4 years on this project. Other people involved are Maurice van Keulen, people from the Netherlands. And we had a student called Jan Rittinger. And he has spent more than half a year in summer at our institute, and his task was to make a code generator layer for Pathfinder to MonetDB. So that's where this came all into a single system that actually works. So basically what he did was create this core to mill translation. Mill is the query algebra of MonetDB, uniting the two systems. So in general, so basically what this slide says is that Pathfinder originally and still is intended to generate SQL, but in this case actually it generates a relational kind of algebra called nil, right?
The blank box over there, would that also be nil?
Yeah, you could actually do that, but would probably not work very well. I'll try to explain that later. So MonetDB, well, you will hear about it a lot in the near future because Martin Kersten is going to be here. But it has been actually well the center point of many of the things we do at COI for the last decade, and we already applied MonetDB because not everybody is working on MonetDB itself, but many other people doing, for instance, multimedia databases or biological databases. They use MonetDB in our group as the prototype. So there has been a lot of work in developing front ends for MonetDB, and so this one for XML is actually one of many. Okay. So MonetDB is currently in open source. You can actually download it. Oh, you will hear. And actually, well, it was released in September, and we plan to release this XQuery stuff in March. So 1st of March, you'll be able to download also this thing I talk about now. But you'll be reminded by all these things regularly by this guy here, who will be here. This is the MonetDB homepage. Surf there and download it. So the main thing is a refresher about the architecture of MonetDB. Well, this is actually architecture of typical RDBMS. So you have your parser module, query rewriting, optimizer, executor, supported by log manager, recovery manager, access methods, and buffer manager. Actually, Monet is a bit different in the sense that it only implements the lowest layers of that. So it's and concentrates actually on query execution, access methods, and buffer management. And so it separates the system architecture in a front end and a back end. Okay. And the language between front end and back end is this mill algebra. And well, this is a very old slide. In the past, we did the SQL front end, ODMG front end, when object-oriented databases were still in vogue. And so this architecture is intended to be able to use a relational kernel for different kinds of data and for different data models and end-user language. And so this exercise is basically making a new front-end Pathfinder that accepts XQuery queries and executes them on top of MonetDB. So what is Pathfinder and what is relational XQuery? Okay. Well, this is XQuery core, which is a subset of the XQuery language. We use an XQuery core subset, which is highly similar to that defined in the formal semantics of the XML definition. So these are the things well, the system does. So it's pretty complete. Actually, what the system lacks currently is user-defined functions mainly, and a lot of built-in functions, which we still didn't do actually. But in general, all the structures are basic structures are there. Okay, in the Pathfinder guys have been doing a lot of work into in storing and executing path steps efficiently when XML documents are stored in relational tables. So everybody who does that uses some kind of a mapping. There are many of those mappings around. Here you see the so-called pre-post mapping. So each node in an XML document gets a number for the entering and the sequence number for the entering and the closing tag. So that's pre and post. And if you draw the nodes in the so-called pre and post plane, then you actually see, as the middle figure, you see the tree structure still present there. And well, the nice properties of the pre-post plane is that if you consider a node F, like there, the 4 quadrants are the major axes. So these are all the descendants of F are here. The following are here, the ancestors are here, and the precedings are here. So this representation allows you to translate XPath steps into range conditions or simple range conditions on a rectangular table. And these range selections, can be supported efficiently using B-trees. So this is a representation that allows relational systems to efficiently execute path steps. So, okay, this was then refined also with something called staircase join, which introduced the notion of not only range selections but also skipping. But I will come to that in more detail later. Actually, in this system of ours, we don't use pre-post. We use pre-size level, which is basically the same thing, because post is pre plus size minus level. And the reason we do that is that in some of the path steps, you can actually skip or optimize better your path steps if you have these size and level separately. Okay, so documents are threaded and put in these pre-post representation relational tables. But that's only one half. Yeah, right. At the moment it does. Yeah. Yeah, this is a good point. Thorsten, who is involved in XQuery, would say to this question, well, Thorsten, who is involved in this, right, would say that XQuery doesn't have any update mechanism. Well, that is, of course, not really a good answer. But I think we'll be looking into ways of leaving free space in the mapping and doing something with that in the future. Currently, we haven't done that yet, so that's on the future work list. I know, of course, that for Microsoft this is highly important. I mean, updates are important, of course. So, right. So the other half of data in an XQuery system is the sequences, because XQuery expressions yield sequences of items, and items can be polymorphic. So here you see, a problem with the sequence is, well, a sequence has order, and relational databases, tables don't have order, but what we simply do is we put another column to this representation which holds the position information. So in this sense, you can create a list or a bag, or an ordered bag of items. Of course, these items are polymorphic. So you want to represent this as tables. Usually, relational database systems don't allow you to have polymorphic columns, but let's ignore this for the moment. Well, this can, of course, well be resolved in some way. Okay, and then what happens is that for all the XQuery constructs, there are translation rules. So all constructs map into transformations on the underlying relational tables. So if you consider this nested for loops, what we do is so-called loop lifting. So, and this basically introduces a third column, get pos and item. We also now get iter in the table representation of sequences. And the iter indicates that in a certain iteration, in a for loop, the value of the expression is a certain sequence. So if you look at the first for loop, you have an iteration over v0. The values of v0 in scope 1 I'm sorry. This is right. This is the value of v0 in scope 0. So in scope 0 you have, this is the value of this is the representation of the sequence 10, 20 in scope 0. So you have only one iteration, and then you have a sequence of 10 and 20. Okay, if you look at the value of v0 in scope 1, then in the first iteration, the value is a single item of 10, and in the second iteration, it's a single item 20. Similarly, in S2, so in the innermost, there are 4 iterations, and v1 has values 100, 200, 100, 200. Okay? So each loop actually introduces a loop relation with only the iter, and which contains all the iterations of that loop. Okay, now v0 also has a value in the innermost scope, and we derive this by having for each nesting level a map relation that maps outer iterations to inner iterations. And basically you get a join with this map, and then a projection that renumbers this the pos values. Okay. And this map basically is the Cartesian product between the inner and outer scope. And if you see, well, the whole expression, then you would have in the innermost scope these two representations of v0 and v1. And then we would have to translate this return statement, and it in the end boils down to a join such that the iterations match up with each other, and then for each iteration you do execute a certain calculation expression, and then you project again and renumber, and then you get this result. Okay. So, like I said, for each XQuery construct there is a relational algebra mapping rule. Actually, this stuff was published in last FieldB. So, for instance, sequences, when you do sequence construction, you get relational union. If you do if then else, then you first evaluate the Boolean expression and then select with that, and possibly do a union, for the to select and union them, if there's also an else body. You saw the for loop, where that's a map with Cartesian product. Calculations become projection expressions. A number of built-in functions, especially the list ones, also map to relational stuff. So for instance, if you have the function first, that was the first value of a sequence, then this is simply a selection on the pos column, where you select pos is 1. Element construction is a hairy one. It's what it does. It creates new nodes, and basically, and it depends on for that a lot on the descendant XPath axis. And the path steps are those selections on the pre-post plane, which are supported by something called a staircase join. The staircase join is kind of semi-join, because it always gives you back ordered subset of the document. It gives back nodes in document order and without duplicates, as mandated by XPath semantics. And it does that in a single pass. So it's like a scan in that sense. But it's actually better than a scan because it does a lot of skipping. So because of the node encoding, it actually can derive it in certain ranges there cannot be any result nodes. And then it jumps over it. Well, that was published in field B before that. And already also evaluated in the Monet context. So you ask yourself, if you do this, what do you get? Oh, you get this. You get quite large trees. So this is XMark query 2. There is a lot of redundancy, common sub-expression. So the actual tree looks like this. But still, these are very, very considerable queries. Okay. Okay, now something about our MonetDB implementation. So in principle, the whole Pathfinder system is able to do this independent of MonetDB. It basically works on the relational model, flat tables. So you have the layers of parsing, normalization, schema import, core generation, simplification, typesetting, core optimization, and only the last one is MonetDB specific, which is mill generation. There is also, but not really functional, SQL generation layer. I mean, in the field B paper, last field B, that described all these mapping rules, there were experiments with DB2. So there is some DB SQL generation as well. Right, so there are actually two modules that are Pathfinder modules. So there's one is the compiler, which is a standalone thing, really. It accepts XQuery queries as input and outputs relational algebra. And there is a runtime module, and the runtime module mainly has the staircase join. So the efficient skipping version of document selection. Also things like XML serialization in it. And the rest is in the MonetDB kernel. Okay, so this is more in detail the way documents are stored. So actually, well, there is what we call this is the schema. And this schema is instantiated multiple times in principle. While currently we create an instance of the schema for each document that is being stored. We call it a document container. So there is the main table is the precise level table. And it refers to, for each node, to one of these other tables. So text, comments, processing instructions. And actually we do that a bit dirty with a single foreign key column and a kind that determines to which of the tables you refer. There's also our qualified names, and attributes are a different table that refer back to the precise table. Okay, what's interesting maybe is when a query runs, there is this loaded document table. And the loaded document table refers to all the containers, because this are multiple instantiations of the schema, called document containers, are all the containers that are currently active for this query. So if this query happens to access 2 XML documents, then those 2 documents are loaded. And there's also a third, or there's also an extra one, which is the transient document container. The idea of separating this out into multiple sets of tables is that when you do elements construction, you're going to create new nodes. Basically, you have to insert new tuples in the precise level tables. And you don't want that multiple concurrent XQueries are going to collide with each other. So that's why each query has its own set of transient tables, so it can safely insert into that without any transaction overhead. Okay. Oh, this is just XML or processing instructions are embedded SQL, or I don't work with them, but in practice it seems that yeah, it's a type of node. Yeah. Okay. So what is special about MonetDB? Yeah, it's this column store, column-wise fragmentation. You know that so tables are actually, relational tables are actually stored in various vertical fragments. Each column has one, and actually these columns are also stored often in a kind of optimized way. So usually, or often we have these OID columns with often densely ascending numbers, and then actually these numbers are not stored. Yeah, it's all called not OIDs, but voids, virtual OIDs. So you get a singular array or a unary array that's very thin. So okay, these voids are actually quite important. So because well, first of all they save you a lot of space, but more importantly for XPath skipping, is that you can access them positionally. So you don't need, if you know the OID of a node, you can go to it without even using the index, because you have positional access to that. That makes staircase join even more efficient. Okay, so these were the documents. Now the items. So items are so these sequences. I mean, sequences are these POS item combinations. So here you see 2 examples. So here X is 20 and 3, and Y is in the first iteration 20 and 2, and the other iteration is 3 and 2. Okay, well, I already said that it's not possible in a relational system to store polymorphic types. So what happens is that there is again a ref and kind representation there. So the ref points to a position in one of the so-called value containers, and the kind determines which type it is, basically. And each query, when it starts, gets its own set for all the basic types of these containers. And as the query runs, values are inserted there, actually double eliminated, so you don't have the same value twice. And when the query is over, these value containers are thrown away again. Okay. I think I'm way ahead of schedule. Don't you want to ask questions? Number of optimizations. And one of them is order prevention. So obviously order is quite important in these plans. XQuery maintains quite strict notion of order. So we encode order using this extra POS column. And often when you do an operation, for instance, in this case, you would have a union, so you would have sequence construction, for instance. So you have an expression that does sequence construction, and in the first iteration you would have a sequence of with value 1, 2, and gets a 3, so you get 1, 2, 3, and here you get a sequence with a single value 10, and you unite it with single 11, you get 10, 11. Okay. So what you need to do, well, basically it can be a relational union. Well, here you do a reunion by concatenation, and you get this. But then you need to renumber this, the positions. And to do this, you use what in SQL 99 is the dense rank primitive. So you introduce a new rank. Well, dense rank for a total table just puts 1, 2, 3, 4, 5, 6, 7 in a column. But you can also do this with a group by. So, and we do the group by on iter. So per iter, it's numbers, the elements 1, 2, 3, 4, 5, etc. So normally this, the implementation of dense rank on the physical level often will enforce that you sort the relation first on iter and pos, and only then you can renumber. Because if you get the values in random order, the pos values in random order, you cannot generate the correct dense sequence ranks. So so often you would need iter pos order on the. You would need to sort this table first, and then you can renumber it. Actually, if you have hash-based implementation of dense rank, that's not necessary. If you keep a hash table with the current rank number for each iter, you can just emit it and increment it. And actually, this kind of ordering, what you need, we call iter given pos. Oh, no, it's the other way around. Sorry for mine. You need pos given iter. Sorry. So you need you need pos given iter. So given an iter, if you take the subset of the tuples as they appear in the table, you want that the pos values appear ordered. That the tuples appear in the desired pos order. Let's say it like that. And but that is actually a kind of ordering property that is not maintained in relational engines at this moment. So, and if you don't do that, then the only way to really enforce this is to sort. And that means that many rules, almost all rules that manipulate somehow these tables, need to renumber. It's very common in all these rules. And then you get extra sorts for this. And that can be very expensive.
Do you compute the pos always after operation?
Yeah, well, you need to, because these things are compiled in isolation. So the next operator that consumes the table is, with a high probability, order dependent. It's XQuery for you. So only, for instance, if you do an aggregation, and we will talk about that, and you know that order is not important, or if it's in the unordered function, so then you don't need to generate pos, but usually you have to generate pos, yes. Otherwise you lose the positional information and you get the sequence without order. Okay. So actually what's in the field B paper is that that they first make a new pos column, which is actually where you guarantee that the things that come here are always larger than here. So you add possibly the max to this, and then you do a sort on these iter and pos columns, and then you get of this, and then you do dense rank, and you replace the computed pos column by a dense rank again. This is what I do. But that is a quite expensive thing, and it introduces lots of sorts in the plan, in the execution plan. Okay, and that is often not necessary actually, because we saw here that if you had just a union that did a concatenation, then actually you got it just right. If you do a hash table dense rank, you would not need to sort. So we actually use recent results by Wang and Cherniak, who define a quite detailed order property system. So that actually includes this iter given pos ordering information. And they define order propagation rules for relational operators. And what they do and what they show then in Postgres is that you can decorate physical plans with these ordering properties. And in the end, this allows you to eliminate a lot of sorts. also in TPCH kind of plans. Okay, so but it appeared, well, first it was very useful to use this work to in the XQuery context. Okay. So we also did a bit of new work. Well, we refined this, and because they didn't really have a use of C1 given C2 ordering properties. We did a bit of extra work here, and we also used something called refine sort. I don't know whether this is in SQL Server. It's a very simple idea. So if you have a relation and it is sorted on a set of columns already, but you want to extend this set of columns, you don't need to resort it entirely. You can do some kind of pipeline sort. You can get a chunk where the already sorted values have an equal value, and only within that small chunk, often, you just use sorting. Because often you get things that are sorted on iter, but not yet on pos, and then you can save a lot of effort. Okay. So basically, that order prevention can happen in two ways. I mean, what we do is the second item here, so generating a physical query plan, and that means that actually the XQuery generator is aware of the properties of the input relation and is aware of the properties of the relational operator that it generates, and already eliminates sort itself. So that is quite easy, actually. So that's what we do. So we don't generate orders if we don't need them. If you would generate a logical query plan, then you would just generate, well, SQL, for instance. Then you would need to do what Wang and Cherniak did. You would need to implement this order propagation inside the optimizer. Otherwise, you would do excessive sorting. So this is, I mean, suppose that you would be interested in doing XQuery in this way, then this would either mean that the XQuery generator would need to generate physical SQL Server plans, or the SQL Server order propagation system would need to be extended, probably. Okay, join recognition. I explained how nested for loops were mapped into iter pos tables that became bigger and bigger in the inner loop by joining the iters with a map, and the map was a Cartesian product. Well, that didn't sound good, and it is not good. So if you have a join query like this from XMark, it is obviously a join, so it's not a nested for loop alone. There is a work condition in it, and you don't want to generate all these intermediate results. So the idea is that instead of generating the Cartesian product of all matching iters, you generate a relation that is smaller than that. It only contains the iters that actually match with each other. So what we now, so if the simple condition exists, so simple work conditions, so equality, or all theta conditions basically, smaller and bigger than, we do a theta join first, and only make a map with the matching combinations. And well, you see for the join queries in XMark, this makes a tremendous difference in performance. Actually, we couldn't even run the bigger sizes, bigger than 10 megabytes XMark with the Cartesian product, which we just went out of bounds.
So if the inner join $p that is dependent on $p, would you still translate into a join?
Yes, I think so.
And what would happen if you had $p in $p give you two anti-collapses, and then you come down to those options? What do you do with anti-collapses?
Well, I mean, the observation here is that it's what we support is not only simple P is T, but there can actually be path expressions or other XQuery expressions nested before we get to the comparison function. So what happens is that in this case, well, I'll just explain it with the graph on the next slide. Is that good? Okay, let me say that this join recognition currently is done on the level of the X core tree. So you have an X core representation of the XQuery and do some pattern matching there and recognize these if-then expressions with two unrelated, unbounded, or independent for variables. And then you replace the inner for query node with a join query node. But actually it's a question whether we should do this on the X-core level or whether we should do this on the relational level. And currently we do it on the X-core level because that was easier for the moment. So, okay, so here is what happens. So you have the sequence that was the left and sequence what was in the right. And what typically happens is that there is some path expression or some other XQuery can actually be a lot of different things or even nested for loop that makes this initial sequence bigger or smaller, but typically bigger. So this is done, and then on the result of the path expression, so could also be an access expression, you have a table with a different shape, but we retain, let's say, the IDs, the IDs of the first sequence. You do the theta join. Theta join could be actually quite big. And then what you are, because for instance with the semantics of comparisons in XQuery are existential. So if there is one element, or if there is only one combination of left iter and right iter that qualifies, then left iter and right iter qualifies. That is so if you do a comparison on two sequences in XQuery, it evaluates to true if there is only one matching, already if there's only one matching combination of values in these. So that's what you get here. So you get possibly lots of matches in a theta join, and then you make this unique again, make it small again. And in the case of theta join, you can actually do better. We do something called join push down here. So if you have predicates smaller, then we can actually make these expanded tables smaller by doing a min and max, and then only generating the unique combinations of matching iters. Okay. And there is something called loop lifted staircase join. That's my last optimization thing. So we had already staircase join. So the staircase join is this scan with skipping, kind of semi-join. And it works on a set of context nodes. So you have a path expression, there is a set of input nodes, and within one sequential scan with skipping, you generate a result. However, in XQuery, this is nice for XPath, but in XQuery you can get nested path expressions. That means that you do not have one context node sequence. For each iteration, you have a different context node sequence. And if you would do staircase join like this in a loop fashion, you would actually need a lot of passes over the document. For each iteration, you would pass again over the document. So what loop left staircase join is a kind of advanced or enhanced staircase join that processes multiple context node lists in a single pass. And in that way, it's more efficient than doing it repeatedly. So here you see the process of, for instance, descendant for the normal staircase join. So you have this list of context nodes. Only one is active at a given time, and you do some kind of merging and possibly skipping, and then for the next you generate other descendants. So this new loop lifted staircase join accepts multiple of these lists, and it keeps some kind of active stack of possibly multiple active nodes for which you generate results. And this allows you to still use only a sequential path. So you see that on the XMark, this actually makes a lot of sense. You see the relative performance with respect to by loop lifting the child and both and descendant. So not much. With
branching. In your statement, for loop lifted status 1,
yes,
branching because you are maintaining multiple branches.
yes.
How do you evaluate?
What do you mean with branching?
Branching means I have some chemical from the state.
Well, the predicates are evaluated afterwards in this implementation currently. So you get a lot of unnecessary results. Well, not always. I mean, for certain kind of tests, we allow a staircase join with filter. So you can pre-execute a filter and only generate nodes that are able to qualify. But it does not work, for instance. We don't have a good solution, for instance, to get the second child or something like that. That's not well supported right now.
Disk activity in this picture, or everything is in
This is in one thing. Yeah.
Everything's in memory.
This is in memory. Yes.
So that is what happens.
What happens if you do this?
What happens if you do this to this? No, the indexing, your indexing structure is all based on the knowledge of the processor architecture and memory and all that.
Well, basically what this as loop lifted staircase join does sequential access through your table. So it could be worse, I would say. You would definitely maybe make a different. Maybe you would not. Maybe it doesn't pay off to skip always. If that means that you will do a seek, maybe it's sometimes better to just go on and do everything sequential. Now this is I don't for this. What can I say? Yeah, the original staircase join was implemented in DB2 and later also. Well, it was the idea of path taps in the pre-post plane was evaluated in DB2, so with I/O, and I think that it was also successfully applied in PostgreSQL. Torsten Groest had a demo in last FieldDB Toronto doing this same staircase join, non-loop lifted staircase join in Postgres. So I don't think it's really that much different, apart from the fact that it will be slower if you need I/O. Okay, so these loop lifted versions of the staircase join, they use typically a stack and exploit access properties dependent on which access to prune, even between iterations. Okay, this is a scalability test. So XMark at various sizes. Yeah, it seems to be linear. Apart from query 11 and query 12. Query 12, by the way, is a bug. It's much like query 11. This plot is not correct. But query 11 is quadratic because it generates quadratically sized output. So it's not really possible to avoid that. We also now we did some more work last couple of weeks, and it also runs now on the 10 gigabyte version of data. But it's an 8 gigabyte machine. I must say that that for XQuery systems around, this is actually 1 gigabyte. I have never seen XMark done on 1 gigabyte system, even not on IO based system. Even yeah, right. Yeah. You will have to read logarithmic scale. This is on a 10 megabyte. So here we compare Pathfinder with XHive and Galax. XHive and Galax are both navigational systems. So they don't do real query optimization. That means that in the joins, which are queries 8 to 12, they have severe problems already. And actually, for Galax, I must say that Galax always parses the document from file. So its performance is actually, for all queries, around 10 seconds. But we subtracted the result of query 13, which is the fastest one, to get an indication of the real execution cost apart from parsing cost. XHive is not a main memory system, but it caches its data. And this is the best of 5 runs. Sorry? I think they're all hot in this case, because in XHive I did it 5 times, and I reported the minimum. So. Well, I said that the navigational systems that don't do join recognition, they have severe problems. I mean, if you get joins, you get a quadratically sized cost for XQuery and XMark. They're very naive. Oh, yeah. Well, Galax cannot scale to larger sizes. XHive actually can, but it cannot do the joins because it's not recognizing joins. And this is another comparison with the Timber system, which I only recently discovered that they, in the last segment, they published full XMark results. And this is seems to be the best system around. And Timber is a tree-based system with 3 algebras and query optimization. The Jagadish group makes this. So here is a comparison between the two. So actually, yeah, well, I just note in which ones Timber is faster than Pathfinder, and Pathfinder is faster than Timber. So it's a bit of a mixed bag. That is the message. But it is comparable somehow. Okay. I think 6 and 7 are large path steps with a node test. And, well, we are going to do this test push down with the Boolean vector. I hope that when we do that, then 6 and 7 will catch him up. It's really hard to say because it's lots of queries, and you have to dig really deep to analyze why one is faster than the other. I don't think so. No, they're not main memory, but they, in the paper which they present, they don't really scale very far. They only do 100 megabytes. So, and I noticed there that their storage seems to be 7 times the data size. Maybe that's related to it because they had a 32-bit machine. I have no idea. Actually, the Monet storage is only 80% in XMark of the document size. Mm-hmm. Well, I think I would like to improve query 6 because we go through all nodes and then we're generating a large list of all nodes that are descendants, and then we're going to test only then which are of a certain kind, and then we eliminate lots of them with the select, and only then we are going to count. Actually, I would like to do the other way around and push down the node kind test, and then but there is not no. I think that staircase, the path steps with the staircase join, they are pretty efficient. That might be an answer. They're really fast. they're sequential and they just speed through the memory indeed. So path steps work pretty well. Yeah. But there is lots of room for optimization, and a good question is where. I mean, now we do just simple heuristics. I mean, the ones I mentioned, and this is not the real answer. So, but in XQuery, it's actually kind of hard. First, you have to recognize the opportunities to optimize, and then you have to decide what the possible strategies are and their cost. So it's actually more difficult than in SQL, when you don't need to do so much work to discover what the query is or where the join is. In XQuery, it's actually pretty hard to do that in the first place. Because I don't really like XQuery, I must say. I mean, if you look at it, these nested for loops, who invented that? Yeah. Okay. End of talk, almost. So the actually surprising thing, if you recall this daunting tree of so many nodes, when you think about that, and that you can actually execute these queries reasonably fast and scalable, I mean, I did not expect that. I didn't expect much of this student project, I must say. So it came out much better than I thought. Of course, we did a number of important optimizations, like loop lifting staircase join makes it 5 times faster. Join recognition, you couldn't do queries 8 to 12 without it. And the order awareness. Actually, order awareness, I cannot really quantify what it brings. So we're actually working on that as well. Because we did right away order awareness, and we do not show what you get when you don't do it.
That's sort of the first bullet it is an existence proof, but for me it's very unusual.
Mm-hmm.
Runtime environment, right? So do you have any sense of what anything this says about commercial relational products and then XQuery?
Yeah, well, I think there is hope. I think, no, but I think,
Monet data structures.
no, that is not necessary, because staircase join, which is the only real extension to MonetDB, has been demonstrated also in relational systems. So it's not, and it's basically a sequential scan, so it's not really very special. And I think you need order awareness. That's very important as well. So somehow you either need to generate, to go in at the physical level with your XQuery translation, or extend the optimizer to deal with all these order properties. Yeah, but you can also do it with a B tree. So if you know that you can skip to node 415, you can do that with a B tree as well. Yeah. Right. Okay, that is true. I mean, that is also very true. So I want to do something with updates here. My idea is a simplistic idea, maybe, of having free zones in your document. Because we did some tests. I mean, what you do with if you have a structure update, you have to basically do element construction from the root, or from well, in general, from at least, well, in general, I think half of the document needs to be written. So it's a sequential path. It's linear in time. It's not acceptable. So so if you have free zones, you can potentially stop lots of the copying at those free zones if you have sufficient free space there. So that's yeah. Well, but you cannot have. Yeah, well, I don't know. Yeah, you cannot have it both ways. I mean, I think even ORT path for me is not the solution. But okay, so this thing will be downloadable and from March 1st, and we'll try to have order by and user-defined function, non-recursive user-defined functions in then, and do some more optimizations. Selection push down. Yeah.
Everything else is done in the path line.
Yeah, yeah. The rest is just algebra generation. Yes. It's all relational algebra. Okay.
You took a query which you could express as simple,
Mm-hmm.
and did the same thing in XQuery with a straightforward representation of data. Then how is performance better?
What do you mean with a straightforward representation of the data?
Well, you pick whatever representation.
Well, so, a schema oblivious one, you mean? I mean, because
you pick whatever you want.
Yeah, okay.
If you have a
Yeah.
SQL database, SQL query,
Oh.
translate the query and the database, whatever we want.
Yeah.
XQuery,
Uh-huh.
then how is the performance compared?
This is a hard question to answer. It depends a lot on what you do, of course, but well, this is I will not be surprised if XQuery in end is an order of magnitude slower than doing the same thing in SQL. I would not be. I mean, and we are happy now with linear performance. This is unacceptable in most environments. If you want to do some kind of web server, I mean, you have to do sublinear performance. So more indexing. Well, I don't think it's impossible. So we just should refine this more and more and more. So yeah.
I think that normalizing your tables or introducing some views so that the overall processing is faster.
No.
Because when you define your query keys and so on,
Uh-huh.
you might find that there are certain characteristics of defining views or denormalizing the tables that can actually
Yeah, maybe, but I wouldn't right away see it. I mean, lots of the query processing happens on the intermediate results, so only the leaves touch, and yeah, you touch the resident data when you go to the document, basically. So typically the path tabs touch the document.
intermediate results, you didn't have to put it in all your tables, right? You have a bunch of results.
Intermediate sequence of items, they don't need to be stored really, and hopefully they are in a pipelinable plan, so that you don't even need to materialize them.
Even if you do XQuery construction.
If you do element construction, then you will need to put those elements in the transient document container. That's what we do at least. Yes. Yeah.
Why only elements?
Well, I mean, if you construct elements, you need to have some document-like representation of those new nodes. So then they go into the. Oh, as well. No, I'm processing instruction as well.
Okay.
Node construction. Yeah. Yeah. Sorry. Yeah. Okay.
I'm going to compare the performance with the
Sorry, once again. With.
I'm going to compare performance of the product with the graphical representation of
Would be interesting. Yeah. I don't think I can report them, but then. No, like I said, I'm very interested in what Microsoft has done and the approach followed. So at least to get some clues, what you did. So maybe later on we can talk about it.
Any thoughts on update?
Sorry?
If you want to update
Yeah.
and then whether your module stay maybe
Well, if you do what I say with updates, so having free zones, then you would introduce a quite dangerous tuning parameter. How much and how often do you need to leave free space? So that is kind of dangerous, of course. But I think it would. I mean, I think there are two reasons why people would like to use an XQuery database instead of an XQuery executor. One is to save the parsing, so to be able to get sublinear performance, hopefully one day. And the other one is to be able to update documents without having to write them out. So I think it's two crucial components, and we want to try something because people will like it, I think, as functionality. So I don't know. Any thoughts? Yeah, I hope. Well, if you tune if your workload matches the tuning parameters, considering the free zones, then it could work out. That's my thing. So user-defined functions, we hope to include them, the non-recursive flavor of them, so the trivial one. So basically by pasting them into the XQuery. But well, I mean, I hear Torsten face things like, we can do recursive functions, but I don't think they will be in the release. Yeah, Torsten, he is the Pathfinder guy. Yeah.
I saw on your XQuery compiler slide, you have type check to the internet, that is typing.
Yes.
Are you using that information for optimization in XQuery?
No.
Please tell us more.
Yeah. Okay.
So, I just want just an overview question. So, how much do you think the implementation benefit from the made specialized column-based data structure for that?
I don't think that it is really crucial. And the thing that is the best thing about Monet for this is these void columns that allow positional access, and that's what makes you don't need a B tree to do a staircase join. If you skip to node 415, you just go there. But apart from that, I don't think, because generally you use all these columns post item anyway, so you can have them together as well.
So how does the staircase join keep you have some
The staircase join, the only thing it needs to know is that the table that's stored conforms to a certain mapping. So it knows that there are not random numbers, these pre, post, and level numbers. And that is the only thing it needs to know. The rest is it's just a table. But if you say, okay, I'm at this node, and I see that its size, so the number of descendants below it, is 42, and I'm doing child, or I'm what I'm doing. Yeah, so I'm in a current child, and I see that the size of that child is 42. Then in 42 position afterward, the next child will be. Yeah. So it uses these values. Hash tables. Hash tables. Monet uses dynamically created hash tables. So if you do certain operations like equality select, then you will get hash tables.
Anything else? Thanks very much.
Okay.